AP Chemistry students, good morning. It's 9:25, and so I'm going to kind of work through some of these ones on this review assignment that tend to be a little bit more problematic. Like I said, I know it's been a while for some of you since you've had this. I want to make sure everybody's cool with what we're doing. So, like let's say for example you have this one on the lead-2 nitrate when you have to write the formula. So remember, the ones that have Roman numerals after them, lead-2, iron-3, copper, okay, those are the ones that have more than one possible oxidation state. So they have they don't know what they want to be. It kind of depends upon the situation. So those tend to be in the middle of the periodic table, okay? Like your alkali metals, lithium, sodium, potassium, those are always going to have an oxidation state of 1+. Calcium, magnesium, okay? Those are always going to have an oxidation state of 2+. And some of those in the middle are always going to have the same oxidation state. Like silver, for example, is always Ag1+. But you have some of them where they can't decide what they want to be. Manganese is the classic example. Manganese can go all the way from 7+ down to 2+, depending upon what it's bonded to. Iron has two possible oxidation states, 3+ and 2+. Copper can be 2+ and 1+. So if you see those with these oxidation states, with Roman numerals, remember that's indicating what that oxidation state is. Now, it used to be, like iron for example, the iron comes from the Greek word, the Fe comes from the Greek word ferrous. So it used to be, in the old style of naming compounds, you'd use ferric and ferrous. So ic, and this is always the same, ic is more, us is less. So ferric would be, this case, iron 3+. Ferrous would be Fe 2+. So you'd always see people in the chemical storeroom going, ic is more, us is less. Ic is more, us is less. So they were trying to figure out, okay, which oxidation state do I need? So then they said, okay, this is stupid. Why are we using ic and us? Let's just change them to Roman numerals. But you only need to use Roman numerals if there is more than one possible oxidation state. So remember, the Roman numerals do not tell you how many atoms there are. It tells you the oxidation state. So like when you have lead-2 nitrate, that's going to be Pb2+, and then you have your nitrate, which is 1-. So this whole thing collectively, this whole polyatomic, has a charge of 1-. This has 2+. You do the cross step, you take this 2, move it over there, okay? So this is just going to be PbNO3 2. All right, no worries there. Iron 3 phosphate is a little bit problematic because with that one you have Fe3+, then you have phosphate, which is PO4 3-. Now, don't do this. Don't take this 3 and move it over here, and take that 3 and move it over there. This needs 3 electrons. This needs 3 electrons. This wants to lose 3 electrons, so it's just FePO4. So don't put, when you write this, just put this as FePO4. Don't put the 3 in the 3. You always write these ionic compounds in the simplest whole number possible ratio. Okay, so that shouldn't be a big deal. Now, when you get down here, this is what I tell you on question number 2, watch for the Romans. This is where you have to decide, hey, do I need to put Roman numerals or not? Well, if you can't decide, if you look on the sheet, the goldenrod sheet, can't find mine right now, but basically, if there's a Roman numeral after it on those list of cations, put a Roman numeral after it. If there's not, don't worry about it. So if you look at this one, like for example, this first one, BeCO2O4. Beryllium only has one possible oxidation state, so there's no need to put a Roman numeral here. Iron and copper, these do have more than one oxidation state, so you need to put Roman numerals here. Zinc only has one possible oxidation state. That's Zn2+. So if you're not sure, go look on that goldenrod piece of paper. That bugs me that I don't have mine. Huh. I swear to God I had one. I must have left it in the back. Okay. Anyway, so if you can find where it has more than one oxidation state, put a Roman numeral. If it only has one possible oxidation state, there's no need for it. Now, on this one where you find the percent compositions, let me give you some hints on these. So this first one with that sodium, that percentage composition of sodium should be around 27%. And on manganese, that percentage should be around 15. So on these, go through, find the entire atomic mass of each one, and then take, like, for example, with this sodium, take the relative atomic mass of sodium, divide that by the total, there you go. Now, like with this one, when you do the oxygens, you've got to take the entire mass of the oxygens. So that's going to be 3 times 16, which is going to get you 48. So this is going to be 48 divided by the total mass to get that percentage of oxygen. Now, when you do this, this is a little bit tricky, so you have manganese 3 dichromate, because manganese is one of these that has more than one possible oxidation state. So when you do this, you have 3 of these dichromate groups. So you need to distribute, in effect, that 3, so you're going to have a total of 6 chromiums, and you're going to have a total of 21 oxygens. So this is a really, really big atomic mass. So this is, you measure out a mole of manganese dichromate, that's going to be a lot because of the fact that it's such a big, massive formula unit because it has such large numbers. Now, let's talk about number 4 on the strontium hydroxide. Here's what you have to watch when you do the strontium hydroxide. Because here's the most common mistake made. You go, oh, strontium hydroxide. That's SrOH2. Or excuse me, SrOH. Here's the problem. Strontium hydroxide is not SrOH2. You have to look at the oxidation states. Strontium is Sr2+, hydroxide is 1-, so you have to write this as SrOH2. Okay? Just because you see this written as strontium hydroxide, just don't go, oh, that's SrOH. You have to look at the oxidation states. So that mole conversion, when you do that 0.238 moles, that should be around 30 grams, and that 48.9 of copper chloride should be around 0.2 moles. So on number 4, this should be around 30. This should be around 0.2. It's an ish, okay, but it should be something in that ballpark. The balancing equations, hopefully you all can do that. That's pretty straightforward. When you get to number 6, where you do this net ionics, so with this one, your 2 products are sodium nitrate and FeOH3. So you have to keep in mind how this is physically happening. This is aqueous sodium hydroxide, so you'd have a solution of sodium hydroxide. You'd have a solution of iron 3 nitrate, so you have what's happening here is that how it's actually existing is these are sodium ions, and these are hydroxide ions, and these are Fe3+, and these are NO3 1-. So this is how these are actually existing in the chemical reaction. So the sodium is going to hook up with the nitrate, okay, which is how you get the NaNO3, and then the Fe3+ is going to hook up with the hydroxide, and that's how you get this. Then you have to decide which one is going to be your insoluble product. Well, there's no way sodium nitrate is going to form a precipitate. Number 1, sodium is a group 1 element, and they're all soluble. Number 2, all nitrates are soluble. You couldn't make sodium nitrate form a precipitate if you tried, because of the fact that they're much more attracted to the water molecules than they are to each other. So this is not going to be your precipitate. Then you look at your solubility rules. Oh, most hydroxides are insoluble. So this is what would precipitate out. So These are still existing as ions in the solution. So these are going to be spectator ions. So your net ionic equation on this one should look like this. It should be Fe3 plus. Now I'm going to do this wrong. Do not do what I'm about to do. Plus hydroxide yields FeOH3. Now, this is wrong. Do not do this. This is wrong. And here's the reason why. Number one, this doesn't balance with charge. This has a charge of 3 plus, that has a charge of 1 minus, so this whole thing ends up with a charge of plus 2. This over here has a total charge of 0. So you have to balance it with charge and the number of particles. So what you want to do is come in here and put a 3 there. Now I've got Fe3 plus 3 hydroxides. Now I have 3 positive charges. I've got 3 negative charges. This balances out to 0. The 3 hydroxides balance out those 3 hydroxides over there. So this is what the net ionic equation should look like. This one is just, the first one is just sodium hydroxide plus FeNO3 is going to yield NaNO3 plus FeOH3. Make sure that you balance those. Okay. On number 7, so I've given you the balanced equation. So like on this one, let's kind of work through one of the more complex ones. Like on that, on 2b, it says how many grams of aluminum chloride can produce 1.08 grams of aluminum. Okay, so this is like one of the more complex ones, so let's just go through this. So you're going to start with that 1.08 grams of aluminum. Now, here's the deal. You're running with the big dogs in an AP chemistry class. This isn't Chem 1, okay? You show me your work. And if you don't like the fact that you have to show me this conversion, I don't care, okay? I really don't. This is about the process. It is not about getting an answer that you put right here, okay? You all have had me before, at least you know my reputation. If all I see is this, and I don't see this, I'm not giving you any credit for that, okay? I'm not. This is about the process, okay? Show me these conversions. I beg of you, show me these conversions. So, you got 1.08 grams of aluminum, so you got to convert that into moles of aluminum. So you know, okay, that's 27.0 grams of aluminum. That's 1 mole of aluminum. Now, at this point, I have moles of aluminum. Okay, if I stop right there, that's what I've got. But what I want is aluminum chloride. So what I've got to do now, don't forget, now I'm going to go up here to the stoich, and now I'm going to look at the coefficients between the aluminum and the aluminum chloride. Okay, so after I get this part done, then I've got to lose my moles of aluminum and roll that into aluminum chloride. So I'm going to go, okay, 2 moles of aluminum, get me 2 moles of aluminum chloride. Okay. Now if I stop now I've got moles of aluminum chloride. It's not what I want. So the next step is to take moles of aluminum chloride and roll that into grams. Now, when you do this, 1 mole of AlCl3, when you're calculating this molar mass of AlCl3, especially with chlorine, okay, or any element, you at least have to use that molar mass, or relative atomic mass, out to the 10th place. So with chlorine, make sure that at a minimum you're using 35.5. Okay, do not round it to 36, do not round it down to 35. Use 35.5. So as a minimum, when you're doing calculations of molar mass, at least go out to the 10th place. At a minimum, go out to the 10th place. Now, you don't have to go out to like the 1000th place or something like that, but at least go out to the 10th place. So, if all goes well on B, your final answer for B should be around 5 grams of AlCl3. Now, here's the assumption that's made on this problem. This is not a limiting reactant problem, because you're assuming that you have enough chlorine gas for this reaction to take place all the way through to completion. So that's going to be one of the key assumptions. So you're just going to assume that this reaction is going to run until the aluminum runs out. Once the aluminum runs out, boom, the reaction is finished. Okay. Your answer to A should be around 1 mole, and your answer to C should be also around 1 gram. So we should go 1, something around 5, something around 1. So that's kind of those range of answers on problem number 2. Excuse me, problem number 7. Okay, now molarity. Remember that molarity is moles per liter. So on this one, you got the 45.87 grams of nickel 2 nitrate dissolved in 250 milliliters of water. What's the molarity? So you got to take this, watch this formula for nickel 2 nitrate, make sure you're using the right formula. Convert that into moles, take the milliliters, divide that by 1,000, get that into liters, boom, you're going to get your molarity. Now, some people like to divide and conquer, some people like to do this as one big stoic problem. I prefer that you do it as one big stoic problem. So start with that 45.87 grams of nickel 2 nitrate, then put the molar mass of nickel 2 nitrate. That's 1 mole of nickel 2 nitrate, and then your end cell here, divide by 0.250 liters. So if you work it all in one step, then you know the stoic is going to work out. So here's grams. This gets used into moles. The last step is that you just put 0.250 liters out here on the end. Boom, there you go. So that answer to 8A should be around 1. So this should be around 1 molar solution. Okay, now let's talk about B. Okay, let's talk about B. So you got sodium sulfate. So first off, you have to realize that sodium sulfate is Na2SO4. Now, pretend that this problem doesn't exist, and we're going to talk about cheese sandwiches. Okay? And you're going, what does cheese sandwiches have to do to this problem? Just stay with me. So let's say that we're going to make a cheese sandwich, and it's going to have 2 slices of bread, and we'll even color code this, and 1 slice of cheese. All right? So that's some really yellow Swiss cheese. So here's the formula. That's B2C. So that's the formula for a cheese sandwich. 2 slices of bread, 1 slice of cheese. Now, here's the deal. We're going to take a bag, and we're going to put in 5 sandwiches. Okay? We're going to put in 5 sandwiches. So we're going to put 5 of these in there, into this bag. So this is like taking solid sodium sulfate and putting it into water. Now, sodium sulfate is very soluble because it's a group 1 element. So it's going to dissociate. It's going to ionize. It's going to dissolve, however you want to think about it. But the same thing is going to happen to this sandwich. So we're going to put these sandwiches in this sack, and then we're going to take them and we're going to shake them up, okay, so that everything dissociates. So we initially had 5 sandwiches per bag. But now when this thing ionizes, we're going to have 10 slices of bread and 5 slices of cheese, because this thing is going to ionize. It's going to separate out. Okay, it's going to decompose. So the concentration of the bread is twice that of the concentration of the initial sandwiches, because it ionizes in a 2-to-1 ratio. Okay? So once I separate these sandwiches, I'm going to have 10 slices of bread, 5 slices of cheese. So the same thing is going to happen here. So when you start with this 24.8 grams of sodium sulfate. 24.8 grams of Na2SO4. Put the molar mass of sodium sulfate here. That's 1 mole. Then here's the deal. Sodium sulfate is going to ionize into 2 sodium ions and 1 sulfate ion. Okay? So this isn't a reaction. Sodium sulfate isn't reacting with anything. It's just ionizing with water. So what's going to happen is that this is a 2-to-1 ratio of sodium ions to sodium sulfate forming the units. So this is a 2-to-1 ratio. So if I stop right here, I have moles of sodium sulfate. Okay, I don't want moles of sodium sulfate. I want the concentration of sodium ions. So I'm going to come over here and go, okay, for every 1 mole of sodium sulfate, I get 2 moles of sodium ions, because that's what I want. I want moles of sodium ions per unit of volume. And so then I'm going to put 0.100 liter here. So look what happens. You're going to start with 24.8 grams of sodium sulfate. Put the molar mass of sodium sulfate here. That's equivalent to 1 mole of sodium sulfate. But when it ionizes, I get 2 moles of sodium ions for every 1 mole of sodium sulfate. And then my last cell, I'm going to divide by the volume of 0.10 liters because of the fact that I want molarity. I want moles per liter. So, if all goes well on B, you should get an answer of, I'm running out of, let me do a little erasing here. So your answer to 3B should be around 3.5 molar. Okay? So that concentration of your sodium ion should be around 3.5. C, that answer should be around 30. And that answer to D should be around 0.1. Okay? So your answer to C should be, I wish I could do that. There you go. So your answer to C should be around 30, and your answer to D should be around 0.1. Okay? This is the simplest one. You just want to know the number of moles. All you have to do is take 0.25 molar, which is moles per liter, multiply that by the volume in liters. The liters cancel out, boom, you get moles. Easy peasy. All right. So let's talk about number 9. So what's the pH of a 0.01 molar solution of hydrochloric acid? Now here's what's important, okay? Here's what's important. Hydrochloric acid is a strong acid. So this is a bigger discussion about strong acids and weak acids. If something is a strong acid, that means that it completely ionizes, okay? So what happens with this, and this is going to be a broader discussion, I'm just going to give you the page 1 of this lecture. So when you take hydrochloric acid and you put it in water, you're going to get H3O plus Cl minus. Now, the reason that we put in the water is because of the fact that this is going to be an aqueous solution. So I'll talk more about this tomorrow. But here's the short version. This is a hydronium ion, otherwise known as a proton, attached to a chloride ion. There's a certain attraction between them. But they're also attracted to the water molecule. Okay, remember that water molecule has that oxygen end, which has that dome of negativity, which is that oxygen end is very negative, and the hydrogen ends are very positive. So basically, that hydronium ion becomes very attracted to that oxygen because they have opposite charges. And the chloride ion is attracted to the positive end. So we write this as H3O plus, okay, and then the chlorine off by itself. So sometimes when you see pH calculations, sometimes you'll see it written as the negative log of your hydronium ion concentration, or negative log of this. Sometimes you'll see it written as the negative log of H3O plus. H plus and H3O plus mean the same thing, okay? So, but here's what's important. It's the negative log of your hydrogen ion concentration. If it's in water, we're going to put it as H3O plus. A lot of times you just see it written as H plus, but it's the same thing. So, if something's a strong acid, okay, if something's a strong acid, what that means is that whatever the concentration is of the HCl is whatever the concentration is of your hydronium ions. So, listen to me, okay, this is going to be hugely important. If it's a strong acid, we say the equilibrium lies to the right. This thing is going to completely ionize into hydronium ions and chloride ions. But this is only true if this is a strong acid. If this was nitric acid, something like that, that equilibrium would lie to the right, and you would have whatever concentration is of the acid is whatever the concentration is of your hydronium ions. So all you have to do, because of the fact that this is a strong acid, okay, on this one, all you have to do, let me get rid of my sandwiches. Never liked cheese sandwiches anyway. So on this one, on number 9, all you have to do is take the negative log of whatever that concentration is 0.015. Now, quick refresher on logs. We're trying to figure out what power I raise 10 to so that I get 0.015. That's what I'm trying to find. So, not to ruin the surprise, but this answer is going to be 1.82. Now, pH, when you write down significant digits on pH, it's a little bit weird how significant digits rules play out on pH. And it's the only time this ever happens. When you're looking at significant digits with pH, the number to the left of the decimal point doesn't count, okay? This is like such a known value that there's no uncertainty here. The uncertainty plays out to the right of the decimal place. So whenever you write a pH value, you cannot go wrong with this. Whenever you write a pH or a pOH, you always want 2 digits to the right of the decimal place. Okay, listen to me. There is no exceptions to this whatsoever. Even if this was exactly 1, you would write this as 1.00. So when you're writing pH or pOH, listen to me. You always put 2 digits to the right of the decimal place. No exceptions. 2 digits over here. Okay? Those. Okay? 2 digits. 1.82. Now, here's how you can make sure that you got this right. And this plays out into this next question. If you want to make sure that you got this right, take 10, okay, and raise it to a negative 1.82, and you should get 0.015. The door swings both ways. So when you calculate a pH, if you really want to make sure that you're right, take 10, raise it to a negative 1.82, you should get 0.015. That's how you can check that you're right. Now, when you get to this next question, I got a pH of 4.57. What's the hydronium ion concentration? Okay? So with this one, I'm trying to figure out what that concentration is. Now, remember, pH stands for negative log. Okay? Negative log. So what you want to do on this one, you want to take 10 and raise that to a negative 4.57, okay? And then this is going to get you this concentration here. So, on this one, because you know what the pH is, reverse the process. Take 10, now you have to raise it to a negative 4.57, right? To a negative 4.57. So there you go. Now, and this answer should be something like 10 to the negative 5th. So, on this next one, what's the pH and pOH of a solution involved 4.5 grams of, oh, I'm sorry, I skipped down one. So on this one, so Solution has a hydroxide ion concentration of 10 to the negative fifth moles. What's the concentration of your hydronium ions and the pH? So remember that auto-ionization constant of water, which is 1.0 times 10 to the negative 14th, equals your hydronium ion concentration times your hydroxide ion concentration. So I've given you the hydroxide ion concentration. That's going to go here. You want to find the hydronium ion concentration. So you're going to take this here, which is your hydroxide, divide that into that auto-ionization constant of water. That's going to get your hydronium ion concentration. And then to get your pH, you're going to take the negative log of that value right there. It's the simplest way to do it. So you should get a pH of around here of 9.4 something. Okay? Now, hopefully, if you look at this, this is going to make sense. If this was neutral water, this would be 1 times 10 to the negative 7th, which would be your hydroxide ion concentration. But this is 2.74 times 10 to the negative 5th, so that means I have a higher concentration of hydroxide ions than I do of hydronium ions. So my pH then is going to be above 7 because I have more hydroxide ions than I do hydronium ions. That's why that pH is going to be above 7. Okay. Now, when you get to this one, okay? So the next one's a little bit trickier because I've got 4.5 grams of lithium hydroxide. So here's the deal. Take the 4.5 grams, change that into moles. You got the volume, okay? Find the molarity. Now, because of the fact that this is lithium hydroxide and it's soluble, so whatever the concentration is of the lithium hydroxide, that's going to be the concentration of your hydroxide ions. So once you get the concentration of the hydroxide ions, there's a couple of things that you can do. I don't care how you work this problem. Once you get the concentration of your hydroxide ions, what you could do is just take the negative log of that and get your POH, and then subtract that from 14 to get your pH. Because your pH plus your POH always add up to 14. That's an option. Once you find your hydroxide ion concentration, you could take that, divide it into 1.0 times 10 to the negative 14th, get your hydronium ion concentration there, and then take the negative log of that. Personally, if it were me, I'd just find my hydroxide ion concentration, I'd take the negative log of that and get my POH, and then I would just subtract that from 14 to get your pH. So if all goes well on that one, that pH should be around 13. That was a horrible 3. Okay? That's even worse. Can't write today. Okay. So this should be around 13. This should be around 1. And those are huge issues, but at least kind of gives you some idea of what's going to take place. On the neutralization, you got lithium hydroxide and nitric acid. And you're going to get lithium nitrate and water. Okay? So anytime you neutralize a strong acid with a hydroxide base, you're always going to get water, and that's solid. So with this one, it's just stoic. You know the volume and the molarity of the base. Start with that. Do your stoic conversions. Roll that into moles. Roll moles into grams. So this answer should be around 1 gram of lithium hydroxide that you're going to need. What you have to watch on the next one, it is HNO3, but now you're going to react that with strontium hydroxide. Okay? So if this gets a little bit trickier to balance, okay, because of the fact that this is going to be SrOH2, you're still going to get water, you're still going to get strontium nitrate, but you have to balance that, okay? So if all goes well on that next one, you should get an answer around 3 grams. So this should be around 1 gram, that should be around 3 grams. On your electron configurations, on that electron dot, remember on that electron dot notation, you're only showing the highest occupied energy level. You should at most, when you do electron dot notation, have at most 8, okay? You will never have more than 8. So if you look at like strontium, okay, not to give it away, but strontium is in group 2, it has 2 valence electrons, that should have like 2 dots. Carbon should have 4 dots. Oxygen should have 6. So you should get something like this. And then that carbon is like that where you have 4. Okay? On this next question, pay attention to the fact that it's a single unpaired valence electron. So on this section here, you should have one answer of 3. You should have an answer of 0. And the rest of them should be 1 or 2. So on this section through here, you should have one that has an answer of 3, you should have one that has an answer of 0, and then the other answers should be 1 or 2. Okay? All right. Redox reactions. Now here's this last page. We talked about this earlier. Leo says GER. So if it loses electrons, it's an oxidation. If it gains electrons, it's reduction. So Leo says GER. So here's what's important here. You have elemental zinc. So I would take a piece of zinc, and you all did this in Chem 1. I promise you did this reaction in Chem 1. You took a chunk of zinc. Anything that's an elemental form has an oxidation state of 0. So this is zinc. It has an oxidation state of 0 because it's the elemental form of zinc. Over here I have hydrochloric acid. Okay? Hydrochloric acid completely ionizes. So that means that hydrogen has an oxidation state of 1+, the chlorine has a state of 1-, zinc has a state of 0. So basically this is a tug of war. So what happens when you get over here, the zinc chloride, the zinc now becomes Zn2+, the chlorine is still 1-, and the hydrogen has a state of 0. So if you look at what happens, nothing changed with the chlorine. Chlorine was 1- over here, chlorine is still 1- over there. Nothing changed. Zinc, because it's the elemental form, has an oxidation state of 0. Hydrogen over here has an oxidation state of 0 because it's elemental hydrogen. It's little bubbles of hydrogen gas. So if you look what happens, this hydronium ion, which is a proton, comes along to the zinc, to those outer 2 electrons in the zinc valence electrons, comes along and says, yo, let's hook up. And these electrons, even though they've been with zinc for a long time, okay, and again, zinc is one of those that's formed in the collapse of massive stars, these electrons go, we're outie, deuces, see ya. So these 2 valence electrons here go and join up with that proton because they have a stronger attraction to that hydronium ion than they do to the zinc itself. The zinc now is sitting there going, dude, man, oh, heartbreak. I've lost my 2 posies, I've lost these 2 electrons. I'm so forlorn. The chlorine comes along and says, I got you, okay? You and me, let's hook up. Because the chlorine is still negatively charged. But now the zinc has a charge of 2+. Like, oh, now that's positively charged. Oh, now we're going to be attracted to each other. The hydrogen zooms off and says, hey, we're deuces. We're going to run off together, and we're going to have H2. So the hydrogen gained an electron. Okay, so the hydrogen gained an electron to turn into hydrogen gas. The zinc lost an electron to turn into Zn2+. Okay? So what you'll see is that metals, oddly enough, tend to lose electrons. So metals tend to be oxidized. Non-metals, okay, like chlorine, bromine, oxygen, they tend to gain electrons, so those tend to be reduced. So when you look at what's reduced, that's your hydrogen, okay? Because it gained an electron to form hydrogen gas. What's oxidized is the metal, so that's going to be your zinc. So metals tend to be oxidized, non-metals tend to be reduced. Now, let's talk about reducing agents and oxidizing agents, because this tends to give kids fits. Your reducing agent, and here, like I said, we're going to talk a whole unit on this. I'm just kind of planting this seed. Reducing agents contain what is oxidized. Oxidizing agents contain what is reduced. So, your reducing agent here is going to be the zinc, because the zinc is what was oxidized. So your reducing agent contains what is oxidized. Now, my oxidizing agent contains what is being reduced. So my oxidizing agent is going to be HCl. On this oxidizing agent, just don't put hydrogen. Your oxidizing agent is the entire compound that contains this. And here's the reason why. If you go into the storeroom, we keep reducing agents completely separate from oxidizing agents. Because if you put them together, they tend to react. So we want to keep them separately. We want these reactions to take place on our terms. So, reducing agents and oxidizing agents are the entire compound. This is like the bottle that contains this substance. Okay? So, we keep them completely separate in the storeroom. We don't want reducing agents hanging out with oxidizing agents because bad things happen. Okay, so there's that answer to that one. Now, weak acid calculations. So, let me here's the difference. Weak acids and strong acids. So I already said strong acids completely ionized. So you put them in with water, like for example hydrochloric acid. So if you take hydrochloric acid and you mix that in with water, you're going to get hydronium ions and chloride ions. And this is going to exist all the way over here, okay? This is how this thing is going to exist. You won't have any of this, and it's all going to be hydronium ions and chloride ions. Now, in contrast to that, like for example, here I have some 0.1 molar acetic acid. Now, if this is acetic acid, and we're going to work with acetic acid a lot, okay? So I'm actually going to jump down here to this next problem where you're trying to find the pH of a 0.02 molar of acetic acid. So we're going to use rice charts a lot. Embrace this concept. Don't fight it, embrace it. The R stands for the reaction, because if you don't know what's happening in the reaction, nothing else matters down here. The I stands for your initial set of conditions. C is your change, and E is going to be what's going to happen at equilibrium. Okay, so this is what the rice chart is, and we're going to use this a lot. Reaction, initial, change, equilibrium. Okay, that's what you've got. So, in this reaction, with this acetic acid, here's what we're going to do. So, we're going to take acetic acid, which is HC2H3O2, and we're going to put that into some water. And what's going to happen is that this water, just like it did with the hydrochloric acid, it's going to pull some of these hydronium ions away. So I'm going to form H3O plus and C2H3O2 minus. Okay? So this is the full-blown way to do this. Now, if you don't like that, the shortcut way to do this, and we're going to get to this just because it's a shorter way to do this, is you can just write it as the acid and put H plus and then your anion. So this is just a shortcut way of writing all of this. For now, like on this one, since you know specifically that it's acetic acid, go ahead and write this whole thing out like this. Later on, once we get into like that we understand what's taking place, then I'll let you shortcut it to here. Now, here's what's important. With this one, we don't write the water, but it's implied that there's water in here. So, here's the difference. If it's a strong acid, and you put that in with water, it completely shifts over here to the right. This is where it's most stable. This is the bottom of the gravitational well. This one, okay, you have very little of this. Most of it is still existing as the molecular form, okay? So what that means is that this is actually more stable here than it is over here. Now here's how you can show this. So here I've got a 0.1 molar solution of hydrochloric acid. Here I have a 0.1 molar solution of acetic acid. Okay, so they're the exact same molarities. So what I'm going to do is that I'm going to wash off my pH probe. Okay, turn this on. And these aren't the most accurate pH probes in the world, but they'll do the trick. So I'm going to put this pH probe in this 0.1 molar solution of hydrochloric acid. And the pH drops to about about 2.5, okay? So when I put the pH probe into 0.1 molar hydrochloric acid, that read about 2.50 as my pH, okay? Now, I'm going to do the same thing with my acetic acid. So when I put that into my acetic acid, even though it's the same 0.1 molar, that pH was reading about 4, okay? So this is my hydrochloric acid, and this was my acetic acid, H3O2. Okay, so here's what I want you to see. Both of these bottles were labeled 0.1 molar. So that's the concentration. 0.1 molar hydrochloric acid, 0.1 molar acetic acid. This pH is 2.5. Now, here's the dichotomy. Is that the lower the pH is, the higher the concentration is of your hydronium ions. Because if I take 10 to the negative 2.5, okay, let me do this. Hold on, let me grab a calculator. Hold on. Okay, never mind, I can't find a calculator. So, if I take 10 to the negative 2.5, trust me, that's going to get me around 0.02. If I take 10 to the negative 4, that's going to give me like 10 to the negative 4th. So, and remember this, the lower the pH is, the higher the concentration of your hydronium ions. So what this means is that even though they're both 0.1 molar, this has a lot more hydronium ions in it than this does. So that's going to be one of the main differences that you're going to see, is the amount of ionization. So here's the deal. So in this situation, I have 0.02 molar solution of acetic acid. Okay? So in this particular problem, this is how this is going to play out. I've got 0.02 molar solution. This is my initial concentration. Now, what we're going to assume is that there are no hydronium ions and there are no acetate ions. So these are going to start off as 0. Okay? Boom. Those are going to start off as 0. So what's going to happen is that some of this is going to ionize. I don't know how much, but some of it is. And I don't know. So I'm going to go minus X. Okay? And then I'm going to go plus X, plus X. So Here's my reaction, acetic acid. It's going to ionize some. Here's my initial concentration of my acetic acid, 0.02. This is going to be 0. This is going to be 0. I'm going to lose some of this. I don't know how much. I'm going to put plus X, plus X. Now, if this had been hydrochloric acid or one of the strong acids, then I would lose all of this, so I would go minus 0.02 because it would completely ionize. And then I would put plus 0.02 over here and plus 0.02 if it was a strong acid. Because by definition of a strong acid, it completely ionizes. So if this had been this is why I'm going to make you memorize the strong acids. So if it had been a strong acid, I'd go minus 0.02, plus 0.02, plus 0.02. But it's a weak acid. So this is just going to be X. So this is going to be 0.02 minus X, X, and X. So here's the story. At equilibrium, this is my initial concentration, and I'm going to lose some of it. This is going to become X. This is going to become X. Now, unless it's a very unique situation where I tell you to worry about it, you do not have to worry about subtracting this X, because this is going to be such a small number that it's not going to change this, okay? So technically this is minus X, but unless I specifically tell you to worry about it, don't worry about this X. It's not there, okay? Just act like it's not there. Unless I tell you to worry about it, don't, okay? Which we'll get into later. So here's what's going to be important. This is this equilibrium line. Now, if you look on your equation sheet, you have Ka equals your hydronium ion concentration times your anion concentration divided by HA. Now, let's talk about this value of K. So anytime you see the big K, that means you're at equilibrium. So I'm just going to begin to plant this seed. Anytime you see K, Ka, Kb, whatever it is, KSP, which we'll get into with solubility later. But anytime you see K, that stands for at equilibrium. So this is going to be important. So at equilibrium, Mother Nature wants these numbers over here mathematically to equal a particular numeric value. Okay? Because Mother Nature likes to be in equilibrium because Mother Nature is lazy. So what we have here, and on this problem, the Ka of acetic acid is 1.8 times 10 to the negative fifth. So I know what my Ka value is. Well, it's 1.8 times 10 to the negative fifth. I know what this number is. At equilibrium, I know that my concentration of my acetic acid is 0.02. Now, technically that's minus X, but it's like taking a drop of water out of the ocean. It's not going to change this. So this is going to be 0.02. So I know this number. I know this is going to be 0.02. Now, at equilibrium, the concentration of my hydronium ions is X. The concentration of my anions is also X. So, check my math, but this is going to become X times X, which gets me X squared. So what I have is my Ka times the concentration of my acid at equilibrium is going to equal X squared. So then I'm going to take the square root of both sides, okay? And then that's going to get me X. So when you do this, you get X equals 6.0 times 10 to the negative fourth as your molarity. So this is important. So this 6.0 times 10 to the negative fourth, okay, that gets me two things. That gets me the concentration of my hydronium ions, and it gets me the concentration of my anions. Now, here's the trick. My pH probe only measures and works on the concentration of hydronium ions. I can't measure the concentration of my acetate ions, but I can find, with a pH probe, the concentration of my hydronium ions. So when you do this, and you get 6.0 times 10 to the negative fourth, then from that, now I can calculate my pH. So I'm going to take, in this situation, here's the concentration of my hydronium ions. Why is the lowering now? That doesn't make any sense. Anyway, here's the concentration of my hydronium ions. That's going to be that I can use to find my pH. So then I'm up here, I'm going to take the negative log of 6.0 times 10 to the negative fourth, and this answer is 3.22. So that pH is going to be 3.22. Now, let me see if I can do this on my phone. Hold on, give me a second. Hold on, I'm trying to take the negative log of... Okay, cool. Okay. Now, here's the difference. If this had been a strong acid, and it would have completely ionized, then at equilibrium, the concentration of my hydronium ions would have been 0.02. I just took the negative log of that, and I got like 1.7. So if it had been a strong acid, the pH would have been 1.70 because it all would have ionized and I would have had a lower pH. But because of the fact that it didn't all ionize, because it's acetic acid, the pH is higher, and that's 3.22. So if it's a strong acid, and we'll get into this later, you don't ever talk about Ka values for strong acids, and here's the reason why. The bottom number here is 0, because if it completely ionizes at equilibrium, this is 0, you're trying to divide by 0, and it becomes undefined. So you'll never find Ka values of strong acids because it becomes undefined. You can find Ka values of weak acids. Okay, now, your percent of ionization. So your percent of ionization is that you take the concentration of your hydronium ions and divide it by the concentration of the acid times 100. So in this case, I'm going to take that concentration of my hydronium ions, okay, which is 6.0 times 10 to the negative fourth. Okay, I found what that is. I divide that by the concentration of my acids, which is 0.02, and then I'm going to multiply by 100, and you get like 3%. Okay? So what this means is that this weak acid ionized at about 3%, which isn't very much. So what that means is that this equilibrium, okay, lies over here. Only 3% of those molecules are actually going to ionize. So, but if it was a strong acid, I would have 100% ionization. So that's going to be the fundamental difference. Weak acids exist mostly in the molecular form. Very little of it exists over here. Strong acids, the equilibrium lies to the right because it completely ionizes and it exists on this side. So weak acids left, strong acids to the right. Okay. All right, now, last one, and then we'll call it good. So here's what's going to happen on percent to formula. So this is kind of the reverse of the problem that you did on the front. So if you look at chemical formulas, that was actually one of the big challenges in chemistry, was that how do you actually figure out the formula? So what we did is that we take compounds and we could break them apart, and then we could figure out the percentage by mass. Now, here's the deal. If you look at the formula for water, start with this. This means one of two things. It either means that you have 2 hydrogen atoms to every 1 oxygen atom, or it also means that you have 2 moles of hydrogen gas to every 1 mole of hydrogen gas. But it is not a ratio of mass. So listen to me. Chemical formulas are a ratio of atoms, or they are a ratio of moles. They are not a ratio of mass. Okay? So here's the easiest way to work this problem. Assume that you have a 100-gram sample of this thing. If you have a 100-gram sample, you would have 25.9 grams of nitrogen, and you have 74.1 grams of oxygen. So what you have to do is convert these into moles. So take 25.9 grams of nitrogen. Molar mass of nitrogen is 14. Okay? And that's going to get you 1 mole. Now, I'm not using 28 grams because I don't know what form this is in. Okay? All I know is that it's 25.9% nitrogen. So because of that, this is why I'm going to use this as N and not N2. Now, if it said, oh, it's nitrogen gas, that would be N2, and I would use 28 grams down here. But this is just 25.9 grams of nitrogen. So I'm just going to put this as 14. Don't put that as 28 because I don't know what form this is in. And then you're going to do the same thing with the oxygen. So you're going to take the 74.1 grams of oxygen, divide that by 16. So with this one you get 1.85 moles of nitrogen, and you get 2.50 moles of oxygen. Okay? Now, here's the deal. What I'm searching for on this problem is this ratio of nitrogen to oxygen. I'm trying to figure out how many moles of nitrogen I have to every 1 mole of oxygen. This is what I'm searching for. What is this ratio? Now, here's the deal. At this point, I know I have 1.85 moles of nitrogen and 2.5 moles of oxygen. So what that tells me is that whatever number goes here with my oxygen has to be bigger than what goes with my nitrogen, because I have more moles of oxygen than I have of nitrogen. So at this point, when I do a division, I'm going to take that 2.50 moles of oxygen and I'm going to divide that by 1.85 moles of nitrogen. When you're doing problems like this, do not round these numbers. Keep a lot of digits out here. Do not round this to like 3 and round this to 2. Don't do that, okay? Keep a lot of digits. So when you do this, you get 2.5. Now here's the problem. I can't have 2.5 oxygen atoms to every 1 nitrogen. I can't have a half of an atom. So what I do is come in here and go, okay, right? Whoa, wrong thing. So I'm going to have 2.5, which is 5 halves. So if you change that to an improper fraction, now this says that I have 5 moles of oxygen to 2 moles of nitrogen. So now, if I look at it that way, now this formula becomes N2O5. Because I got 5 moles of oxygen to 2 moles of nitrogen. If that had been 1.5, it'd be 3.5. Now, if this worked out to be exactly 2, then it would just be NO2. If it had been 3, it would have been NO3. Okay? But because it was a fraction, that's why I changed it to an improper fraction. Here's my ratio of 5 to 2. Okay. Last problem, and then we're done. So on that last problem on 13, you're told that you have a molecular mass of 216 grams per mole, and you want to find the molecular formula. So remember, you have 2 types of problems or formulas. You have empirical formulas, which is the simplest whole number ratio, and then you have the molecular formulas, which actually tell you the structure. So here's the classic example. So like you could have CH4. Okay, so that's like an empirical formula, CH4, right? One carbon to 4 hydrogens. Now, the molecule of this might actually be C2H8. So this molecule with 2 carbons and 8 hydrogens, this is what it actually is built as. But it has this ratio of CH4. So this would be like the empirical formula. That's going to be the molecular formula. Now, your molecular molar mass is always a multiple of your empirical molar mass. So what you're going to do is come up here and find the molar mass of your N2O5. So if you do that, you take 2 nitrogens and 5 oxygens, you get 108. So what we're saying is that 108 grams per mole times X is going to equal 216 grams per mole. So if you do some division, you get X equals 2. So what that means is that I'm going to take 2 and multiply that by each one of these. So this is going to become N4O10. So the actual molecular formula, which is the actual compound, how it exists, is going to be 4 nitrogens to 10 oxygens. Now, here's how you can tell that you got this right. Assume that it's N4O10. Find the molar mass of N4O10. If that molar mass is 216, you did it right. If that molar mass isn't 216, you did it wrong. So, I'm out. Hopefully that answers everybody's questions. If you have some more questions, you can ask that in class tomorrow. But let's call it a day.